If you, like us, have ever found yourself deep into a research project, maybe hours in, dozens of tabs open, you know that feeling, right? Where you're just
Yeah.
drowning in information.
Absolutely. It's not just finding the information, it's managing it all without, well, losing the plot completely.
Exactly. And that feeling, that's actually a huge problem for the AI agents we're building to help with these kinds of long, complex web tasks.
Yeah, that information overload, that's the real bottleneck. We see these sophisticated LLM-based web agents, tested on benchmarks like browse comp or wide search.
Which are designed specifically for these long, multi-step reasoning chains.
Right. And they often fail, not because they aren't smart, fundamentally, but because they just collapse under the weight of all the context they're trying to track. It's a context management failure.
So the big question is, how do you build an agent that doesn't just drown? How can it handle hundreds of steps? That's what we're digging into today.
And we're looking at a really interesting paper from Tanguy Deep Research and Alibaba Group. They're introducing something called AgentFold.
AgentFold. Okay, and the core idea is moving context management from just being a passive log.
Exactly, into an active, almost cognitive process. They call it proactive context management.
And it's inspired by human memory.
Yes, specifically this idea of retrospective consolidation, how we sort of mentally tidy up and summarize our experiences after the fact.
Okay, so our mission today is to unpack this AgentFold approach.
And see how they managed to get a significantly smaller model. We're talking a 30 billion parameter model here.
Which is, relatively speaking, not huge these days.
Not at all. But they got it to outperform models that are like 20 times its size.
Just by being smarter about memory.
Sure.
That's fascinating. Okay, let's start with the problem itself. What are the current approaches doing wrong?
Right. So when an agent is doing a complex search, it has to remember its thoughts, its actions, what it saw, all that history.
And the standard way, the sort of default.
That's typically the React framework. Think of it as append only. Everything just gets added to the end of the history. Reason, action, observation, tack it on.
Okay, the upside is you lose nothing. Perfect recall, in theory.
In theory, yes. Information integrity is perfect. But the massive downside is context saturation. It just grows and grows.
How bad does it get?
Well, they found that after just 100 turns in one of these complex tasks, the history could easily hit 84,000 tokens.
84,000 tokens. Wow, that's... You're not going to find anything important in that, are you?
It's like digging through a landfill, exactly.
Yeah.
The critical signals get buried in
Yeah.
noise. The model starts making mistakes, forgetting instructions, basically getting lost because the context window is just crammed full of irrelevant stuff.
It's spending all its effort just trying to read the prompt.
Precisely. So, okay, that's one problem. The other main approach tries to fix the volume issue,
Yeah.
fix summarization. At every single step, the agent tries to summarize the entire history up to that point. Keep it neat and tidy.
Okay, that sounds cleaner, keeps the token count down. But
Mm-hmm.
summarizing everything, every step, that feels inherently risky. You might throw away something crucial, right?
You absolutely hit the nail on the head. It introduces this huge risk of irreversible information loss, and it compounds.
How badly?
Well, think about it. If there's even a tiny, say, 1% chance that a key detail gets lost in one summarization step,
Okay.
after 500 steps, which isn't crazy for these tasks, the chance of that original key detail still being there, it drops to something like 0.66%. Basically, it's gone.
So you're choosing between drowning in data with React or potentially losing the vital clue with fixed summarization? Neither sounds great.
Not ideal at all. And that's where AgentFold comes in with a different philosophy.
Right, the dynamic cognitive workspace idea. Less like a log file, more like a metal scratch pad.
Exactly. And the structure reflects that. Instead of one giant context block, it's partitioned.
Okay, break that down for us.
So you've got the static stuff that doesn't change,
Yeah,
the user question, the available tools, pretty standard.
makes sense.
But then you have two dynamic memory parts. First, the latest interaction. Think of this as your immediate working memory. It holds the raw details, action, observation, explanation, but only for the very last step. High fidelity, but very recent.
Got it. The immediate present.
And second, the really crucial part, the multi-scale state summaries. This is like long-term memory. It holds curated, abstracted summaries of past steps or sequences of steps. The consolidated knowledge.
Ah, okay. So it keeps the raw, messy present separate from the neat, summarized past. But could that cause problems? Like, if the summary is too abstract, does the agent forget why it reached that conclusion?
That's a great point, and that's where the active process is key. AgentFold doesn't just use the standard perceive, reason, act loop.
It adds a step.
Yes. It's a perceived reason fold act. That fold step is explicit. It's where the agent decides how to manage its context.
Yeah.
It looks at the current state, the goal, and chooses how to update its summaries before it acts again.
So context management isn't an afterthought, it's part of the core decision loop. The agent is learning how to remember effectively.
Precisely. It's actively curating its own memory.
Let's get into the mechanics then. This folding directive, it's actually part of the agent's output, alongside its thinking and the action it takes.
Yes, exactly. Memory management becomes a first-class output. And this directive has two main modes operating at different scales.
Okay, what are they?
First is granular condensation. This is the default sort of day-to-day mode. It takes just the latest interaction, that single most recent step.
The working memory bit.
Right. And it folds just that into a compact summary block. Think of it like time stamping and filing away that one step, maybe tagging it like compressed step 5.
So it preserves the detail of that step, but tucks it away neatly so it doesn't clutter the immediate workspace?
Exactly. It protects the fine-grained detail from getting lost, like in fixed summarization, but also prevents it from immediately adding to the noise. It mitigates that compounding loss risk we talked about.
Okay, but if you only did that, wouldn't you just end up with a really long list of tiny summaries? Still potentially noisy?
Good point. That would eventually become unwieldy too. That's why there's the second mode, deep consolidation.
Deep consolidation sounds more substantial, like cleaning out a whole drawer instead of just filing one paper.
That's a perfect analogy. Deep consolidation takes the latest interaction plus a whole chain of previous summary blocks, maybe representing several steps, or even a whole subtask that just finished, and fuses them all into a single, higher-level abstract summary. For instance, compress step 5 to 9.
Ah, so this is how it handles, say, a dead end in the research, or when it finally finds a key piece of info after several tries.
Exactly. It's used to abstract away noisy intermediate steps that didn't lead anywhere, or to package up the conclusion of a successful subtask. It cleans up the clutter and creates structure in the long-term memory.
The paper had a great example of this, right? The GPS coordinates task.
Yes, that really illustrates deep consolidation well. The agent was trying to find GPS coordinates for some location.
And it got stuck.
Seriously stuck. It's been 11 steps, steps 6 through 16, trying different websites, search terms, Yelp, TripAdvisor. Just hidden dead ends. 11 steps of failure.
Okay, normally that would just be 11 steps of noise added to the context history. Difficult to ignore.
Right. But what AgentFold did at step 17 was recognize this pattern. It triggered a deep consolidation.
And what did that look like?
It took that entire 11-step failed sequence and folded it into one single summary block. The summary basically said, look, multiple attempts, step 616, to get GPS coordinates failed. No coordinates found.
Wow. So it effectively pruned those 11 steps of noise into one useful conclusion. That approach didn't work.
Precisely. It clears the decks, it allows the agent to learn from the failure, shift its strategy, and move on without getting bogged down by the details of how it failed for 11 steps. It's active memory editing, driving better reasoning.
Okay, the theory sounds really elegant. Active memory management inspired by humans, but does it actually work? When you put this AgentFold model, the 30B one, up against the big guys?
The results are genuinely striking. AgentFold 30B A3B, that's the specific version fine-tuned on Qwen 3 30B, basically sets a new standard for open source agents in these complex browsing tasks.
Okay, let's put numbers on that. Remember, you're comparing a 30 billion parameter model against giants, some nearly 20 times bigger.
Right, so on BrowseComp, the English benchmark, AgentFold gets 36.2%.
36.2%. How does that stack up?
It's huge. It beats much larger open source models like DeepSeek v3.1671b, which scored 30.0%. And maybe even more impressively, it beats leading proprietary models like OpenAI's O4 Mini, which got 28.3%.
Wow, so it's not just about scale anymore. Smarter architecture's winning.
It really suggests that, especially for these long horizon tasks, architectural innovation seems key right now.
And was it just that one benchmark?
No, it performed well across the board. On wide search, which is broader, it got 62.1%, the best overall score reported. And it even did well in Chinese, getting 47.3% on BrowseComp ZH. So it seems generally capable.
Okay, better results are great. But you mentioned the context size earlier. This folding must have a massive impact on efficiency too, right? Like fewer tokens means less compute, less memory.
Oh, tremendously. Looking at the context, token count really tells the story. With AgentFold, because it's actively folding and consolidating, the context size grows really slowly. It stays under 7,000 tokens even after 100 turns.
Under 7K after 100 turns. And the standard React agent.
That one just keeps growing, almost linearly. Remember, It hit 84,000 tokens by turn 100 in their tests.
So wait, AgentFold's context is like 92% smaller.
Yeah, on average, over 84,000 tokens smaller by turn 100. That's a massive difference.
What does that mean in practical terms, like VRAM?
They estimate it saves nearly 7 GBs of VRAM per inference instance just at that 100 turn mark. That makes running these agents much more feasible.
And it helps with handling even longer tasks, presumably.
Absolutely. They showed that some bigger models like GLM 4.53555B kind of hit a wall. They saturated and failed beyond about 64 turns because they just ran out of context capacity. But AgentFold, its accuracy kept improving steadily, all the way up to 256 turns in their tests. It demonstrates this robustness for really long, complex sequences of hundreds of steps.
This really has been eye-opening. It feels like AgentFold proves a really important point. You don't always need brute force scale. Building in smarter, more human-like cognitive abilities like actively managing your own memory can bridge that performance gap.
I think that's the core takeaway. It's not just about having knowledge. It's about understanding it, organizing it, applying it. Giving the agent the power to shape its own internal workspace seems key to making them robust and scalable for complex reality. We're seeing LLMs evolve from just processors to, well, self-managing knowledge systems.
It definitely changes how we should think about building these agents, which leaves us with a really interesting thought for you, the listener, to ponder.
Right now, AgentFold learns how to fold using supervised fine-tuning. Basically, it's learning from human examples of good folding strategies.
Which works incredibly well, as we've seen.
But what if? What if you trained it using reinforcement learning, RL? Let the agent discover the optimal folding policies on its own, through trial and error, optimizing for long-term task success.
So instead of just following rules for memory management, it would invent its own potentially much better ones.
Exactly. How much more efficient, how much more powerful could these agents become if they were truly autonomous learners, not just of the world, but of their own internal cognitive processes? That feels like a very exciting next step.